So, on the HR diagram, then, you would expect to see, and this is where they are, the blue luminous variables are up here, hypergiants. This actually is the light curve of Eta Carinae, and you can see where it just jiggles up and down and then has a massive outbreak and then kind of settles back down again. T Tauri stars are located over here, stars that are just dropping onto the main sequence. And this is the actual light curve of T Tauri. You see they're very erratic in their behavior. Now, these eruptive variables, when you see them plotted on HR diagrams, the ones that you see out there, this says luminous blue variables, and that's where Eta Carinae would be. You do not see S Doradus on there. You do see down, it does have the T Tauris located just above the main sequence right in here. And it says right here, dwarf novae. That's wrong. That's incorrect. You will see a lot of misleading and incorrect HR diagrams out there. Be careful. Know enough of what you should be seeing to not be misled or confused by erroneous information. I'm going to show you another one next with even more incorrect things on them. Over here, this is actually the only HR diagram I could find that actually had an S Doradus instability strip on it. And here's Eta Carinae today. This is where it was in 1890, and this is when it had the great eruption about 140 or so years ago in the late 1800s. That's where it was on the HR diagram. But pay attention to, this is the log 10 of the luminosity relationship here. So pay attention to what the axes are telling you. A cataclysmic variable is W49b, a type 2 supernova event that has a black hole in the center. This is what it looks like in radio. This is what it looks like in infrared. The radio was from the Very Large Array. The infrared is from Palomar. And we have various X-ray, Chandra X-ray ones. This is of the oxygen, the silica in distribution. This one shows the pink as the ion distribution, because we can just look at one element at a time if we want to. And then a composite of all those put together, which shows you why we need missions in all wavelengths, because every one of those wavelengths is being produced by a different process. And you need to see all of those processes to understand what's going on. This is not a typical symmetrical kind of type 2 supernova event. For some reason, it was very energetic in the polar regions, but something went on that it wasn't as energetic equatorially. Was that some instability within the collapse itself? Was it because there was something in the interstellar medium around it? We don't know, but it does have a black hole in the center. And here's another one that does not look like your typical type 2 supernova collapse either. Not a nice round remnant with your little stellar core in the middle. This is Vela, which is this bubbly mass. All of this bubbly stuff, that's what's left of the Vela supernova remnant. And right here is an X-ray image of the pulsar that's located in the center. And if you look at this little time-lapse movie of the pulsar, you can see the north jet and the south jet around the rotational axis. You can see the matter and antimatter particles spewing out along the rotational axis. And down here, you can just see this south pole one kind of wiggling back and forth. Well, when you look at that wiggle, it's because the pulsar is actually precessing. You know, the Earth precesses in a 26,000-year cycle. Well, this pulsar is rotating about 11 to 12 times a second, and it has a precessional period of only 120 days. Here are some, quote, typical, unquote, type 2 supernova light curves. And there are three different kinds, actually. We have the plateau kind, we have the slowly descending kind, and we have the rapidly descending variety. And the colored in sections are the averages of all of those within plus or minus 2 sigma to show you that there is a lot of variation in even one different type of eruption like type 2 supernova events. This is a type 1a supernova event from previous years. You know, if you've been doing this, you know that those type 2 supernovas are the core collapse of a massive star, but the type 1a's are the thermonuclear destruction of a white dwarf. This is Tycho's supernova event. Now this one's kind of what you would think would be a, quote, typical looking type 1a. There is no stellar core, of course. The white dwarf was totally destroyed. This is all of the fusion products are here. The remnant is all you see. And this is the shock wave, outer edge of the shock wave from the event. And you'll see this odd little kind of curvy circle down here. Well, that actually is the material that was stripped off from the companion star when the white dwarf exploded, because obviously it exceeded Chandrasekhar's limit, so it has a companion star that it was accreting material from. So when it went, it did a little damage to its companion star, stripped some of the material off, and this is the shadow of that debris, and the site of the explosion was right there. So the Chandra illustrators here here's the site of explosion, here's where the companion star was in its orbit around the white dwarf when it went thermonuclear and stripped the material from the companion star, and this is where it is right now in the shadow, and they have discovered the companion star. This one is not so, quote, typical, unquote. This is has the sexy name of G 1.9 plus 0.3. This is probably the youngest one that we know of so far. It happened about 140 years ago, and you can see from its position that it's really embedded within the dust and the gas very close to the center, the plane of the galaxy, so it would not have been seen by anyone at the time. The Chandra data is in blue, the very large array, the radio data is in orange, and as you can see, is like nothing in the middle. So why do we have this really bizarre configuration here? Well, you know, if we were looking at this only in optical, we wouldn't even see it because it isn't producing anything in the optical part of the spectrum. So that's why we need multi-wavelength observations. And this blue stuff that's colorized blue on the outer edge, that's the iron, which is moving at about 4 million miles an hour. Now, the iron was manufactured last during the thermonuclear event, during the fusion process, and it's slower moving and in the middle, but something happened. This was sort of a two-stage explosion. It started to explode. There was some kind of hesitation for who knows how long. Strange and magical things happened, and then it finished exploding. So the stuff that was closest to the middle, the iron, got accelerated at much more energetic speed than the initial part of the explosion, and so it has actually overrun the earlier fusion products of this process. So the iron is actually on the outer edge. So this is a very atypical. But then what is typical? So type 1a events can also be used to measure cosmological distances because they start with a white dwarf. And we know what a white dwarf is. We know how much mass it cannot exceed 1.4 solar masses. So we know the exact amount of energy it's going to produce. And so the absolute magnitude for a type 1a supernova event is minus 19.5. And because a thermonuclear event is so much more energetic than a core collapse, you can see them much further and further away. You can actually use them to determine the distances to galaxy clusters.